that we have done base to power exponents of integers and fractional powers. We've also talked about radicals. Let's look at a new mathematical object, polynomials, that we briefly mentioned when we were looking at the first few lectures when we talked about numbers. So if you look at our counting numbers in the expanded form, the 3, 2, and 4 are called coefficients of 10 squared, 10 to the 1, 10 to the 0, respectively. If we allow the coefficients to be any real numbers, so if 3, 2, and 4 are any real numbers, and then we replace the tens with x's, then we have an example of a polynomial in one variable. The 3, 2, and 4 are the coefficients, and the degree of the polynomial is 2 because that's the highest power that appears in this expression. So a monomial is a product of real numbers and variables which are raised to whole number exponents. So you can't have negative exponents or fractional powers. The real numbers in the term are called the coefficient of the monomial, and the sum of all the exponents in the variables are called the degree of the monomial. So here's an examples of monomials. These two monomials are of one variable monomials. The degree of the first one is 100, degree here is 5. If you look at this one, it has multiple variables in it, and the degree is going to be addition of the exponents of all the variables. So 3 and 5 added together will give you 8. So here are examples of different kind of monomials. The square root 2, negative 5.34, and this fraction here are called the coefficients of the monomials. This is a little bit of dry subject because we're just doing definitions, but it is important for you to understand what this terminology really means. A polynomial is a finite sum of monomials. So if you have one or more monomials combined together with addition or subtraction, you end up with the example of a polynomial. The degree of the polynomial is defined to be the highest degree of the monomials that appear in the polynomial. So here's an example. This is example of one variable polynomial where the degree is 100 because the highest power appearing there is 100. All of these numbers that sit in front of the variable, square root 2 plus 5, negative 4, 15, are coefficients of the polynomial. Here's another example where you have a multivariable polynomial. Here the power is 1 and 1, so this monomial has power degree of 2. This monomial has a degree of 6, 2, and 4. This one has 10 and 2. So that's your highest degree term. So the degree of this polynomial would be 10 plus 2 equals 12. So we are looking at the degree across all the monomials, and so the coefficient of this polynomial is going to be negative 34, 5, negative 4.1. We can also have polynomials with complex coefficients. So negative 4 plus I is a complex number, and that is a coefficient of x and z to the third. So this is an example of a polynomial which allows for complex numbers as coefficients. An algebraic term is a product of numbers and variables using any algebraic operations. And you're not restricted to exponents to be whole number. So algebraic expression is the sum of one or more. There should be sum of one or more algebraic terms. All polynomials are examples of algebraic expressions, but the reverse is not true. For example, here's an example of there are two polynomials and you have a rational term. Rational means numerator, denominator. So here we have an algebraic term that's not a polynomial. Here's another example of algebraic expressions that are not polynomials. Because if you look, there's a denominator x to a variable. In other words, if you were to rewrite this, this would be 3x to the negative 4, and you cannot have integer powers. You need whole number powers to be a polynomial. Same thing here. Negative 4 is an integer power for the variable, which is not allowed to be a polynomial. Here's an example. Here you have 1 over square root 5, but this is still a real number, and so you still have this algebraic expression is also a polynomial. So your next video log set is asking you whether the algebraic expressions below are polynomials or rational expressions. Rational expressions means you have a fraction and the numerator and denominator are polynomials. So go ahead and identify whether it's a polynomial or algebraic expression. And if it is an algebraic expression, if it is a polynomial, then tell us what is the degree of that polynomial as well. So let's talk about polynomials as a mathematician would. How do we represent arbitrary polynomials? So in order to define arbitrary polynomials, we use variables to denote the coefficients. So for example, if I wrote ax cubed plus bx squared plus cx plus d, where I allow a, b, c, d to be any real numbers, and a has to be non-zero real number so that you don't have zero here, then this would be a generic polynomial of degree 3. Because I'm allowing a, b, c, d to be any coefficient, and then these are the placeholders for the different x powers. As you can see, if I wanted a 100-degree polynomial, I'm going to run out of letters for the coefficients because there's only 26 letters in the alphabet. But mathematicians are clever. They can have infinitely many variable placeholders by using subscripts. So for example, if I wrote a subscript 100, and represent that as any real number, coefficient of the 100th degree term, and so on, I will never run out of variables. I can say A1, A2, A3, A100, A1000. I can have thousands of variables, infinitely many variables. So if I wrote this polynomial as A subscript 100, that's just saying this is a variable, and then x to power 100. So this is the coefficient of x to power 100. This is a coefficient of x to power 99, and so on. And so this is a generic polynomial of degree 100. In general, a polynomial of degree n is then represented as a subscript n, x to power n. Then the next one will be one less than n, like 100, 99, and so on, all the way to the constant term, which is a sub 0, where a sub n is non-zero, and all the other numbers are any real number. All the coefficients are real numbers, but the first term, the highest degree term, has to be non-zero so we can talk about its degree. So polynomials are used in physics, chemistry, business, and lots of other disciplines. So some of the specific polynomials have names to them. As we saw, monomials, here are some examples of monomials. Then we have binomials, which is sum of two monomials. So if you have just two terms, we have a binomial. So a polynomial with two terms is called binomial. Here's another example. A linear polynomial means degree 1 polynomials. So here's 3/5 x plus 4. Here's a degree 1 polynomial in two variables. Quadratic degree 2 polynomials. So 3x squared. So remember, the degree of this polynomial is 2, so we call it a quadratic polynomial. Here's a quadratic polynomial in two variables. Cubic polynomial would be degree 3 polynomials. So these are just some examples of polynomials that people work with frequently, and so therefore have specific names to them.